In the far reaches of our solar system, Venus is a world of extremes. Its air is so thick it flows like liquid, temperatures exceed the melting point of lead, and surface pressure can crush submarines. Over 50 years ago, the Soviet Union's Venera missions ventured into this inferno, becoming the first human-made objects to enter another planet's atmosphere and transmit data. Their discoveries, hidden in Cold War archives, carry a chilling warning for Earth. So before we go deeper, hit like, subscribe, and tell me in the comments what you think this really means. And if you want to help this message reach others who still wonder, share it on X, Facebook, Reddit, or even just in your group chats. You're the reason this search is alive. Thank you for keeping your eyes open. Krov. What if the future of Earth is written in the fires of Venus? The Venera program began in 1961, just 4 years after Sputnik. Early hopes of a mild climate on Venus were dashed when Venera 4 entered the planet's atmosphere in October 1967, revealing temperatures up to 250 and pressures of 22 atmospheres. Mariner 5 confirmed these extremes, dispelling the myth of a tropical paradise. Soviet scientists persevered, designing landers to withstand Venus's harsh conditions. Venera 7, launched in 1970, survived a freefall and transmitted data for 23 minutes, revealing a surface temperature of 465 degrees and pressure of 90 atmospheres. Subsequent missions pushed technological limits, returning the first images from another planet's surface and uncovering intense geological activity. Venus's runaway greenhouse effect, driven by a thick carbon dioxide atmosphere, serves as a stark warning about unchecked climate change on Earth. Billions of years ago, Venus might have had oceans and a temperate climate. Understanding its fate could help us avoid a similar outcome for Earth. The Venera program, despite numerous setbacks, symbolized the Soviet Union's technological ambition during the Cold War. Part 1. First Light. On June 8, 1975, Venera 9 touched down on the surface of Venus, marking the first time humanity had successfully landed a spacecraft on another planet. This mission was a monumental achievement, representing years of relentless effort and innovation by Soviet engineers. The lander was a marvel of engineering. A spherical titanium hull cocooned within 12 centimeters of thermal insulation, a composite honeycomb material designed to withstand the furnace-like conditions of Venus. This insulation was not just a barrier but a lifeline, protecting the delicate electronics from temperatures that could reach up to 465 degrees, hot enough to turn lead into a molten puddle. Inside, a large thermal accumulator filled with lithium nitrate trihydrate, weighing approximately 15 kilograms, worked in tandem with a circulating fan, distributing heat evenly to prolong the lander's operational life in an environment that seemed designed to destroy it. Every component was meticulously engineered to endure the crushing pressure and infernal heat, a testament to human ingenuity in the face of adversity. The true innovation of Venera 9, however, was its camera system. Designing a camera that could function on Venus was an engineering challenge of unprecedented scale. The cameras had to be shielded inside the pressurized vessel, yet they needed an unobstructed view of the alien landscape outside. The solution was elegant yet complex. 2 cameras were mounted inside the lander, each equipped with a periscope that extended through a thick quartz pressure window. These periscopes allowed the cameras to scan their surroundings, rotating to capture a 180-degree view of the Venusian surface. Each camera was fitted with a protective lens cap designed to pop off after landing, revealing the first-ever glimpses of another planet's surface. The periscopes were a feat of precision engineering, each one meticulously calibrated to ensure no dust or debris from the Venusian atmosphere could obscure the lenses. The quartz windows, too, were a marvel, capable of withstanding the immense pressure and heat while maintaining optical clarity. The cameras themselves were designed to operate in temperatures as high as 60 degrees Celsius, a remarkable achievement given the technology of the time. Before the lander separated from its carrier spacecraft, it was pre-cooled to 10 degrees, a stark contrast to the inferno it would soon encounter. The descent began at about 50 kilometers above the surface, a journey that relied solely on air braking for the final stretch. This decision was strategic. The dense Venusian atmosphere posed a risk of tangling or damaging a parachute, so the lander was designed to descend without one. It touched down at a speed of 7 to 8 meters per second, a gentle jog by Earth standards, but enough to rattle the lander's systems. The landing site was carefully chosen based on radar maps from earlier missions, targeting a relatively flat region to minimize the risk of the lander tipping over. Once on the ground, the lens caps were programmed to eject, but only one did. This small mechanical failure would later be addressed in future missions, but for now, one camera was enough to change history. Venera 9 transmitted the first photograph ever taken from the surface of another planet, a grainy black and white image that revealed a rocky, desolate landscape unlike anything ever seen on Earth. The ground was littered with sharp-edged stones, some as large as half a meter across, their jagged shapes hinting at a violent geological past shaped by volcanic activity. The rocks appeared layered, possibly formed from ancient lava flows, a familiar yet alien sight. Above, the sky glowed with a bright diffuse light, the result of sunlight filtering through Venus's thick perpetual cloud cover. The light level was about 14,000 lux, comparable to an overcast day on Earth, casting long, eerie shadows that stretched across the alien terrain. The atmosphere itself was a hazy yellow-orange, the result of sulfur compounds scattering the sunlight, creating a perpetual twilight that obscured the horizon. The lander operated for 53 minutes before the heat finally overwhelmed its systems. In that short window, the interior temperature rose from 10 degrees to 60 degrees, a testament to the harsh conditions of Venus. But the mission didn't end because of thermal failure. It ended because the orbiter relaying the signal back to Earth moved out of range, a limitation of the mission design rather than a failure of the lander itself. Just 5 days later, Venera 10 followed, landing in a different location and transmitting images for 65 minutes. Like its predecessor, only one of its two cameras functioned, a recurring issue that would later be resolved. The images from Venera 10 showed a landscape subtly different from Venera 9. The rocks were smoother, the soil finer, suggesting a distinct geological history shaped by different forces. The smoother rocks hinted at the possibility of erosion, though not by water, as Venus lacks liquid surface water. Instead, the erosion might have been caused by the corrosive effects of the supercritical carbon dioxide or the scouring action of wind-blown dust particles. The soil itself was a fine, powdery substance, likely the result of millions of years of weathering by the harsh Venusian environment. Despite the brevity of the mission, the data returned by Venera 10 was invaluable, providing scientists with a glimpse of a world that had previously existed only in theories and speculation. For the first time, humanity could see what the surface of Venus looked like, and it was nothing like what anyone had imagined. The black and white images from Venera 9 and 10 were groundbreaking, but they were low resolution, offering only a partial glimpse of an alien world. The Soviets wanted more. In 1978, Venera 11 and 12 were launched, carrying improved instruments, including more sensitive atmospheric sensors and a new type of drill designed to penetrate deeper into the Venusian soil. However, neither spacecraft's lens caps released and no images were returned, a frustration that underscored the challenges of operating in such a harsh environment. Despite this setback, the landers transmitted valuable atmospheric and surface data for 95 and 110 minutes, respectively. This data revealed that the surface pressure was even higher than previously thought, reaching up to 92 atmospheres, enough to crush most terrestrial materials. The temperature was also confirmed to be a scorching 437 degrees C, reinforcing Venus's reputation as a hellish world. The atmospheric sensors detected traces of sulfuric acid vapor, a corrosive substance that further complicated the engineering challenges of future missions. The sulfuric acid was part of a larger atmospheric cycle, where sulfur dioxide released by volcanic activity reacted with water vapor to form dense clouds that shrouded the planet. The breakthrough came with Venera 13 and 14, launched in 1981. These landers were similar in design to their predecessors, but featured key improvements. Soviet engineers had developed new heat-resistant materials and electronics that could function in extreme temperatures, including exotic lubricants based on molybdenum disulfide and microscopic metal flakes designed to work at temperatures up to 1000 degrees C. The amount of lithium nitrate phase change material was increased to 20 kilograms, providing better thermal regulation. Critically, the camera system was redesigned to ensure the lens caps would eject properly, a small but crucial adjustment. The landers were also equipped with more robust communication systems, allowing for faster data transmission back to Earth. This was essential, as the short operational window on Venus required maximum efficiency in data collection. The landers were also outfitted with spring-loaded drills, capable of penetrating several centimeters into the Venusian soil to collect samples for analysis. On March 1, 1982, Venera 13 landed on the eastern edge of Phoebe Regio, a highland region of Venus characterized by its rugged mountainous terrain. Both lens caps ejected successfully, a triumph of engineering over the harsh Venusian environment. The lander immediately began taking panoramic photographs, capturing the alien landscape in vivid detail. Unlike the black and white images from earlier missions, these were in color, revealing a world that was both familiar and utterly alien. The landscape was dominated by bedrock outcrops surrounded by dark, fine-grained soil, a stark contrast to the rocky terrain seen in earlier missions. The rocks had a brownish-orange tint, a result of the unique minerals present in Venus's soil. The sky above was a murky yellow-orange, the result of sunlight scattering through sulfur compounds in the atmosphere, creating a perpetual haze that obscured the horizon. The soil appeared to be a fine, powdery substance, likely formed from the weathering of volcanic rocks over millions of years. The images also captured faint streaks in the soil, possibly caused by the movement of wind-blown particles across the surface. But Venera 13 did something else unprecedented. It recorded sound. Microphones on the probe captured atmospheric wind noise as it descended and after it landed, providing the first audio record of another planet. These recordings also picked up sounds from the lander's own equipment, the impact of landing, the pyrotechnic ejection of the lens caps, and their impact on the ground, the drilling apparatus cutting into the surface. The sound is eerie, a low rumbling wind, mechanical clunks and whirs, the hiss of the Venusian atmosphere at 92 atmospheres of pressure. It doesn't sound like Earth, it sounds exactly like what it is. An alien world, a place where the laws of physics are familiar, but the environment is utterly foreign. The recordings revealed that the wind on Venus, though slow, had a powerful force due to the dense atmosphere. The sounds of the lander's equipment echoed strangely in the thick air, providing a haunting soundtrack to the first human-made sounds on another planet. The audio data also hinted at the possibility of distant thunder, a phenomenon that scientists had long theorized but never confirmed. Venera 13 operated for 127 minutes, more than 2 hours, a remarkable feat given the extreme conditions. The temperature outside was 447 degrees, hot enough to melt zinc. The pressure was 9 megapascals, equivalent to 89 Earth atmospheres, enough to crush a submarine at the deepest point of Earth's oceans. And throughout that time, the lander was drilling into the surface, analyzing soil samples, measuring atmospheric composition, and photographing its surroundings. A mechanical arm drilled into the ground and deposited samples into a hermetically sealed chamber maintained at 30 degrees and 0.05 atmospheres of pressure, conditions closer to those on Earth than on Venus. An X-ray fluorescent spectrometer analyzed the composition, revealing that the rock was lucidic basalt with high levels of potassium and magnesium, but only 1.5% sodium. This was Earth-like rock, volcanic in origin, similar to the basalts found on Earth's ocean floors, suggesting a shared geological history between the two planets. The soil samples also contained traces of rare minerals, hinting at a complex geological past shaped by processes both familiar and alien. The spectrometer data also revealed the presence of small amounts of radioactive isotopes, suggesting that Venus may still have active volcanism, with lava flows occurring as recently as a few million years ago. The radar maps from Venera 15 and 16, launched in 1983, further deepened the mystery of Venus. These maps revealed long rift valleys, volcanic features, and ridges and grooves that appeared to be the result of tectonic deformation. This was unexpected. Without water to lubricate tectonic plates and without a magnetic field to suggest a molten core, Venus shouldn't have plate tectonics. Yet the radar images showed features that looked remarkably similar to tectonic activity on Earth, hinting at a dynamic geological history that scientists are still working to understand. The radar data also revealed vast lava plains, some stretching for hundreds of kilometers, indicating that Venus had experienced massive volcanic eruptions in its past. These eruptions may have been so powerful that they resurfaced entire regions of the planet, a process that could explain why Venus lacks the impact craters seen on other terrestrial worlds, like Mars and Mercury. The radar images also captured enormous coronae, circular features up to 2,000 kilometers in diameter, formed by plumes of hot magma rising from the planet's interior. These coronae are unique to Venus and provide further evidence of the planet's ongoing geological activity. Here's where things get even stranger. At the surface of Venus, carbon dioxide isn't quite a gas anymore. It's something else, a supercritical fluid. Carbon dioxide becomes a supercritical fluid above a critical point of 73 atmospheres of pressure and 300 Kelvin, about 30 Waraditos. A supercritical fluid has properties of both a liquid and a gas. It can dissolve materials like a liquid, but it flows and expands like a gas. It's dense like a liquid, about 67 kilograms per cubic meter on Venus, which is 6.5% the density of liquid water on Earth. At Venus's surface, with temperatures of 460 degrees and pressures of 92 bars, the carbon dioxide is well into the supercritical region. This means that Venus's surface is technically covered by a supercritical ocean, a sea of carbon dioxide that doesn't have waves or a distinct surface the way water does, but behaves more like a fluid than a gas. It transfers heat extremely efficiently, which is why the temperature on Venus barely changes between day and night. The supercritical carbon dioxide acts as a thermal buffer, distributing heat across the entire planet, creating a world where the boundaries between liquid and gas are blurred. This supercritical fluid also plays a role in shaping Venus's geology, possibly dissolving and redepositing minerals in the planet's crust, contributing to the formation of its unique landscapes. The supercritical fluid may even interact with the planet's interior, influencing the movement of magma and the formation of volcanic features. Some researchers have suggested that this supercritical ocean may have once been even more liquid-like earlier in Venus's history when pressures might have been higher. Computer models indicate that under certain conditions, clusters of gas-like bubbles could have formed in the supercritical carbon dioxide, creating structures that look like soap bubbles covered in a thick layer of liquid. Whether this ever happened on Venus is unknown, but the idea that Venus once had seas of liquid or near-liquid carbon dioxide is scientifically plausible. The geological features seen in the radar maps, the rift valleys and plains, could potentially be explained by the movement of this supercritical fluid across the surface, carving channels the way water does on Earth. The possibility of a once liquid Venus challenges our understanding of what it means for a planet to be habitable, blurring the lines between the familiar and the alien. If Venus had liquid on its surface, even if it was carbon dioxide, it raises intriguing questions about whether life could have evolved in such an environment, adapting to conditions that seem inhospitable by Earth standards. The supercritical ocean may have created niches where extremophile organisms could have thrived, using the unique chemistry of Venus to sustain life in ways that are entirely unfamiliar to us. The story of Venus doesn't end with what we've already discovered. It's a story of what we still don't know and what we might find in the future. As technology advances, future missions to Venus could reveal even more about its geological history, its atmospheric composition, and the mysterious processes that shape its surface. Already, proposals for robotic landers and even human-crewed missions are being discussed, driven by the desire to unravel the secrets of this enigmatic world. Venus, once thought of as Earth's twin, has proven to be a planet of extremes, a world that challenges our understanding of what a planet can be. Its story is far from over, and the light it sheds on our own planet's future is just beginning to be understood. The next chapter of Venus exploration promises to be even more extraordinary, a testament to human ingenuity and our unquenchable thirst for knowledge. Future missions may include orbiters equipped with advanced spectrometers to study the composition of Venus's atmosphere in greater detail, or landers designed to survive longer on the surface, perhaps even for days or weeks. There are even concepts for balloon-like probes that could float in the upper atmosphere, where conditions are more Earth-like, providing a unique perspective on the planet's dynamic weather patterns. These balloons could carry instruments to study the chemistry of the clouds, search for signs of lightning, and map the winds that circle the planet every few days. The lessons learned from Venus could also inform our understanding of exoplanets, worlds orbiting other stars. Many of the exoplanets discovered so far are similar in size to Venus, and some may have comparable atmospheres. By studying Venus, scientists can develop models to predict the conditions on these distant worlds, helping us identify potentially habitable environments beyond our solar system. Venus may hold the key to understanding not just our own planetary neighborhood, but the broader cosmos. The more we learn about Venus, the more we realize that it is not just a hellish world, but a planet of profound complexity, one that continues to surprise and challenge us. Its story is a reminder that the universe is full of mysteries waiting to be uncovered, and that our quest to understand it is far from complete. Venus, with its supercritical ocean and alien landscapes, stands as a testament to the incredible diversity of worlds that exist in our universe, each one a unique laboratory for exploring the possibilities of life, geology, and atmosphere. As we continue to explore this enigmatic planet, we are not just learning about Venus. We are learning about the limits of our own imagination and the boundless potential of the cosmos. Part 2. The Unknown Ocean. At Venus's surface, carbon dioxide isn't just a gas, it's a supercritical fluid, a state of matter that blurs the line between liquid and gas. This supercritical ocean covers the entire planet, transferring heat so efficiently that the temperature barely changes between day and night. But what if this ocean was once even more liquid-like? Computer models suggest that under certain conditions, clusters of gas-like bubbles could have formed in the supercritical carbon dioxide, creating structures that look like soap bubbles covered in a thick layer of liquid. Could Venus have once had seas of liquid or near-liquid carbon dioxide? The idea is scientifically plausible, and it raises intriguing possibilities about the planet's past. Imagine a Venus where the supercritical fluid was denser, more viscous, and capable of supporting complex chemical interactions. This hypothetical ocean could have allowed for the formation of carbon dioxide-based geological structures such as carbonate deposits or even unique mineral formations that have no analog on Earth. The fluid's ability to dissolve and transport minerals might have shaped the planet's surface in ways that are now hidden beneath its crushing atmospheric pressure. The geological features seen in the radar maps from Venera 15 and 16, long rift valleys, volcanic features, and ridges and grooves, could potentially be explained by the movement of this supercritical fluid across the surface, carving channels the way water does on Earth. But the mystery deepens when we consider the atmosphere itself. The Venera missions provided the first comprehensive ground truth measurements of Venus's atmosphere and surface. Venera 4 confirmed that carbon dioxide makes up 96.5% of the atmosphere. This was the first direct measurement of Venus's atmospheric composition. It also detected nitrogen at around 3 to 4% by volume and trace amounts of water vapor, sulfur dioxide, and other gases. Venera 5 and 6, launched in 1969, further refined these measurements, revealing that the atmosphere was even denser than previously thought, with surface pressures reaching 90 times that of Earth's. These missions also detected the presence of sulfuric acid clouds, which extend from 30 to 70 kilometers above the surface, forming a perpetual haze that blocks nearly all sunlight from reaching the ground. The acidity of these clouds is so extreme that it dissolves most organic compounds, making it impossible for Earth-like life to survive in the upper atmosphere. But the atmosphere of Venus is not static. Recent data analysis suggests that nitrogen concentration decreases from about 3.5% at 7,000 meters altitude to nearly zero at the surface. If real, this gradient could indicate active outgassing of carbon dioxide from Venus's crust, possibly from low-level volcanic activity. The flux of CO2 required to maintain this gradient is comparable to diffuse volcanic emissions from systems like Yellowstone on Earth. This would mean Venus is still geologically alive. If Venus is indeed volcanically active, it raises the question of how this activity shapes its atmosphere and surface. Volcanic eruptions on Venus would release massive amounts of sulfur dioxide, which could explain the thick sulfuric acid clouds observed in the atmosphere. These eruptions might also release water vapor, which would quickly dissociate in the harsh conditions, contributing to the planet's runaway greenhouse effect. The heat generated by volcanic activity could also drive tectonic processes, reshaping the surface over time, but the questions don't end there. Did Venus ever have a magnetic field to protect it from solar wind? Did it once have oceans of liquid water? And if so, what caused the runaway greenhouse effect that turned it into the hellscape it is today? These are questions that haunt us, not just because of what they tell us about Venus, but because of what they might reveal about our own planet's future. Observation. The lack of a magnetic field on Venus means that its atmosphere is directly exposed to the solar wind, which strips away lighter gases like hydrogen and oxygen over time. This process, known as atmospheric escape, has likely played a significant role in the loss of water from Venus's surface. Without a magnetic field, the planet's atmosphere has been gradually eroded over billions of years, leaving behind a dense, carbon dioxide-rich environment. Interpretation. Venus's current state may be the result of a catastrophic climate shift triggered by a combination of factors, including volcanic activity, the lack of a magnetic field, and the intense solar radiation it receives due to its proximity to the Sun. This shift could have transformed a once habitable world into the inhospitable place we see today. Understanding this process could provide valuable insights into the long-term stability of Earth's climate and the potential consequences of unchecked greenhouse gas emissions. Speculation. If Venus once had liquid water oceans, they might have supported the emergence of life. However, the runaway greenhouse effect would have boiled these oceans away, leaving behind a desiccated planet with a crushing atmosphere. The possibility that Venus was once habitable raises profound questions about the fragility of planetary environments and the conditions required for life to thrive. It also underscores the importance of studying Venus to better understand the limits of habitability in our solar system. The supercritical ocean of Venus remains one of the most mysterious and tantalizing features of the planet. Its unique properties challenge our understanding of planetary processes and offer a glimpse into a world that is both alien and eerily familiar. As we continue to explore Venus, we may uncover clues about its past, and in doing so, learn more about our own future. Part 3. The Descent. The descent through Venus's atmosphere is an ordeal unlike any other. Venus's atmosphere is about 93 times more massive than Earth's, extending much higher and structured in distinct layers, each with its own characteristics. At the top, above 100 kilometers, the atmosphere is thin and relatively cool, a stark contrast to the inferno below. This is where spacecraft first encounter drag during entry, a delicate phase where the angle of attack must be precise to avoid incineration or skipping off the atmosphere entirely. The Venera probes hit the atmosphere at speeds around 11 kilometers per second, and the initial deceleration was violent, subjecting the craft to forces up to 170 times Earth's gravity. The heat shield had to absorb temperatures exceeding 11°C as friction converted kinetic energy into heat, a process that turned the shield into a glowing fireball streaking through the alien sky. The heat was so intense that it could vaporize metal, and the shock waves generated by the entry could disrupt the probe's trajectory, making precise navigation a life-or-death calculation. Between 70 and 50 kilometers altitude, the landers entered the cloud deck, a realm shrouded in perpetual twilight. This is where the sulfuric acid droplets are concentrated, forming a corrosive fog that would quickly destroy exposed metal. The clouds are not uniform. They're layered with different particle sizes and compositions at different altitudes, creating a complex vertical structure. Some Venera probes carried nephelometers, instruments designed to measure cloud particle density and size. The data showed that the largest droplets, up to 10 micrometers across, are found in the middle cloud layer around 50 to 55 kilometers. These droplets scatter sunlight in ways that make Venus appear bright and featureless from space, concealing its true nature. The clouds also contain trace amounts of other chemicals, such as hydrochloric acid and hydrofluoric acid, which add to their corrosive properties. Below the clouds, the atmosphere becomes increasingly dense and hot, transitioning from a hazy yellow to a murky brown as the sulfur compounds thicken. At 30 kilometers, the pressure is about 10 bars, and the temperature is around 200 degrees Celsius, hot enough to boil water, but still far from the extremes of the surface. This is where the parachutes were designed to detach, allowing the landers to fall faster, using only air resistance. The final descent from 30 kilometers to the surface took about 30 to 40 minutes, a journey into an abyss of rising heat and pressure. During this time, temperature and pressure increased exponentially, doubling roughly every 10 kilometers. The landers were transmitting continuous measurements, building a detailed profile of the lower atmosphere that remains one of the most comprehensive datasets ever collected from Venus. One of the key discoveries was the wind profile, a phenomenon that defies easy explanation. At altitude, Venus's atmosphere rotates around the planet in just 4 Earth days, a phenomenon called superrotation. Winds at the cloud tops reach speeds of 100 meters per second or more, whipping the clouds into a frenzy that circles the planet 60 times faster than its actual rotation. But as you descend toward the surface, the winds slow dramatically. By the time you reach the ground, wind speeds are only about 0.5 to 1 meter per second, barely enough to stir dust. This creates a paradox. The upper atmosphere is moving incredibly fast, but the surface is nearly still. What drives this motion? How is energy transferred between layers? These questions remain partially unanswered, though some researchers believe convective cells and atmospheric waves play a role. Theories suggest that the intense solar heating at the cloud tops creates temperature gradients that drive the superrotation, while the dense lower atmosphere acts as a brake, slowing the winds to a crawl. The interaction between these layers is so complex that it has been compared to the intricate dynamics of Earth's jet streams, but on a far more extreme scale. But the descent revealed more than just wind patterns. The Venera missions also measured the composition of the atmosphere at different altitudes, uncovering a dynamic chemical environment. Carbon dioxide dominates everywhere, making up 96.5% of the atmosphere, but the concentration of trace gases changes with height. Sulfur dioxide is more abundant at mid-altitudes, peaking around 30 kilometers, where it plays a crucial role in the formation of sulfuric acid clouds. Water vapor, though scarce, is slightly more concentrated near the surface, accounting for just 30 parts per million, but hinting at a past when water may have been more abundant. These gradients provide clues about chemical reactions happening in the atmosphere and possible interactions with the surface. For example, the presence of sulfur dioxide suggests ongoing volcanic activity, as it is quickly destroyed by sunlight and must be replenished from below. Similarly, the trace amounts of water vapor hint at a cycle where water is continuously stripped from the surface by the intense heat, only to be broken down by UV radiation in the upper atmosphere. The sulfuric acid clouds themselves are a testament to this chemical interplay, as they form through a series of reactions involving sulfur dioxide, water vapor, and sunlight. The descent also revealed the presence of other intriguing compounds, such as carbonyl sulfide and hydrogen chloride, which further complicate our understanding of Venus's atmospheric chemistry. These compounds are likely the result of complex interactions between volcanic outgassing, photochemical reactions, and the planet's unique environmental conditions. For instance, carbonyl sulfide is thought to be a byproduct of volcanic activity, while hydrogen chloride could be produced through the interaction of hydrochloric acid and the planet's surface minerals. The presence of these gases in varying concentrations at different altitudes suggests a dynamic system of chemical exchange, where materials are constantly cycled between the surface and the atmosphere. This system is further influenced by Venus's slow rotation, which allows for extended chemical reactions in the upper atmosphere due to prolonged exposure to solar radiation. The resulting chemical profile is unlike anything found on Earth or Mars, making Venus a unique laboratory for studying the extremes of planetary chemistry. And yet, despite everything the Venera missions taught us, Venus remains deeply mysterious. We don't know if Venus ever had liquid water oceans. Computer models suggest it might have billions of years ago when the sun was cooler and Venus's atmosphere was thinner. If that's true, then Venus was once habitable, at least in the sense of having liquid water on its surface. We don't know what caused the runaway greenhouse effect that turned Venus into the hellscape it is today. Was it volcanic activity releasing massive amounts of carbon dioxide? Was it the loss of water, which would have helped remove CO2 from the atmosphere? Did Venus ever have a magnetic field to protect it from solar wind, and if so, when did it lose it? These questions are not merely academic. Understanding Venus's past could help us predict Earth's future in a warming climate. Venus's current state is a stark reminder of how a once habitable world can be pushed beyond the brink, transformed into an uninhabitable inferno by processes that may have parallels to our own planet's climate trajectory. We don't know much about Venus's interior structure. Without seismometers operating on the surface for extended periods, we can't measure how heat and material move through the planet's mantle. We don't know if Venus has a molten core or if its core has solidified. And we don't fully understand the atmosphere, the superrotation, the planet-wide wind patterns, the sulfur cycle, the complex chemistry happening in the clouds. All of these phenomena remain poorly understood, and unlocking their secrets could rewrite our understanding of planetary evolution. For example, if Venus's core is still molten, it could imply that the planet retains significant internal heat, which might drive ongoing geological activity such as volcanism. Conversely, if the core has solidified, it could explain the absence of a global magnetic field, leaving the planet vulnerable to solar wind stripping of its atmosphere. The interaction between the core, mantle, and atmosphere is a critical area of study, as it could shed light on how planets evolve over billions of years. But the story of Venus is not just a story of mystery. It's a story of human ingenuity and perseverance in the face of impossible challenges. The Venera missions were an achievement that deserves more recognition than it gets. In the West, they were overshadowed by the space race to the Moon and the Viking landers on Mars. But in terms of pure engineering difficulty, landing on Venus and operating there for even a few minutes was as impressive as anything NASA accomplished. The Venera probes were designed to withstand pressures equivalent to diving a kilometer deep in Earth's oceans and temperatures hot enough to melt lead. They were equipped with cameras, drills, and soil samplers that functioned flawlessly in an environment that would destroy most electronics in seconds. The Venera 13 lander even returned the first color images from the surface of another planet, a feat that required unprecedented engineering innovation. The images revealed a desolate landscape of jagged rocks and dusty plains, bathed in the eerie orange glow of the filtered sunlight. These images were not just scientific data, they were a window into another world, a glimpse of the alien surface that had long been hidden behind Venus's impenetrable clouds. The last signals from Venera 13 and 14 faded out in 1982, but their legacy endures. The landers are still there on the plains of Venus, slowly being corroded by the atmosphere. One day, perhaps a future mission will find them, these ancient artifacts of humanity's first steps onto another world's surface. For now, they rest in the heat and the darkness and the crushing pressure, monuments to what humans can achieve when we refuse to accept that something is impossible. Their designs have informed every subsequent Venus mission, from the Soviet VeGa balloons that floated in the upper atmosphere in 1985 to NASA's proposed Da Vinci Plus probe, which aims to descend through the clouds in the 2030s. The VeGa balloons, for instance, provided valuable data on wind speeds and atmospheric dynamics, while future missions like Da Vinci Plus aim to build on this legacy by exploring the chemistry and geology of Venus in even greater detail. But the future of Venus exploration may lie in the technologies NASA is developing. Silicon carbide electronics, advanced phase, change thermal systems, long-duration power supplies. If these technologies mature, we could have landers and even rovers operating on Venus for weeks or months. A seismometer operating on the surface for 60 days could detect Venus quakes, measure crustal movements, and determine whether Venus's interior is still molten. A rover could travel kilometers across the surface, studying different rock types and searching for evidence of past water. We could finally answer the fundamental question: is Venus dead, or is it still alive? The answer could reshape our understanding of planetary habitability and the delicate balance that allows life to thrive. For instance, if Venus is found to have ongoing geological activity, it could imply that the planet is not as dead as once thought, potentially harboring subsurface environments that might support extreme forms of life. Conversely, if Venus is confirmed to be geologically inactive, it would reinforce the idea that the planet has long since passed the point of no return, a cautionary tale for Earth's future. The story of Venus is far from over. It's a story of a world that was once different, a world that may have had oceans, a world that may have had a climate not unlike Earth's. Something changed. And until we understand what that something was, we won't fully understand our own planet's future. The fires of Venus may hold the key to our own survival, a stark reminder of what can happen when a planet's climate spirals out of control. As we stand on the precipice of our own climate crisis, Venus serves as both a warning and a testament to the power of human curiosity and resilience. The descent into its atmosphere is not just a journey through alien skies, it's a journey into our own future. By studying Venus, we are not merely exploring another planet, we are exploring the potential fate of our own world, a world that, like Venus, hangs in the balance of its own climate destiny. Part 4. The Long Shadow. The last Soviet probe to reach Venus's surface was Venera 14 in 1982. The Vega missions in 1984 were the final hurrah, and then nothing for decades. Why? Part of the answer is economics. The Soviet Union was facing increasing financial strain in the 1980s. Space exploration, while prestigious, was expensive. Venus missions, with their complex engineering requirements and high failure rates, were particularly costly. By the mid-1980s, Soviet priorities were shifting. The Mir space station program was taking up resources. Plans for Mars missions were being drawn up. Venus fell out of favor. The collapse of the Soviet Union in 1991 essentially ended Russia's planetary exploration program for years. Budgets were slashed, expertise was lost as engineers retired or moved to other fields. The infrastructure that had supported the Venera program decayed. Entire departments dedicated to Venus exploration were disbanded, and archives of data from previous missions were left to gather dust. The economic turmoil of the 1990s saw Russia's space ambitions narrow to maintaining its presence in Earth orbit, with the Mir station serving as a symbol of national pride amidst widespread hardship. Meanwhile, NASA's focus had shifted to Mars. The Viking landers in 1976 had captured the public imagination. Mars seemed more hospitable, more Earth-like, more likely to have hosted life. Venus, by comparison, seemed like a dead end. There was also a technological barrier. The Venera missions had pushed 1970s and 1980s technology to its absolute limit. To go beyond 2 hours of surface operation would require fundamentally new approaches, new materials, new electronics, new power systems. Those technologies didn't exist yet, so Venus was left alone. The harsh conditions on Venus, surface temperatures exceeding 870 degrees or 465 degrees C, and atmospheric pressures 92 times that of Earth, made it a daunting challenge. The Venera landers, despite their groundbreaking achievements, were essentially one-use devices, transmitting data for brief windows before succumbing to the inferno. The idea of sustained exploration seemed almost impossible with the tools available at the time. But the story of Venus is not just a story of the past, it's a story of the future. NASA has announced 2 missions to Venus launching later this decade. Da Vinci Plus, the deep atmosphere Venus investigation of noble gases, chemistry, and imaging, will drop a probe through the atmosphere in 2031. During its hour-long descent, it will analyze trace gases, water vapor, temperature, and pressure. In its final 20 minutes, as it falls through the cloud deck, it will photograph a highland region called Alpha Regio before impacting the surface. VERITAS, the Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy mission will use radar to map Venus's surface in far higher resolution than ever before, creating detailed 3D relief maps. It could identify safe landing sites for future missions. The European Space Agency has approved Envision, a radar mapping orbiter that will study Venus's surface composition and internal structure. Russia has been discussing Venera D, a return to Venus that would include both an orbiter and a lander. The lander would have a mission lifetime of about 3 hours, based on battery capacity and traditional thermal management. Da Vinci Plus and VERITAS represent NASA's first dedicated missions to Venus in over 30 years, marking a renewed commitment to unraveling the planet's mysteries. Da Vinci Plus will not only analyze the atmosphere, but also search for signs of past water activity, while VERITAS will produce global topographic maps with resolutions as fine as 250 meters per pixel. Envision, slated for launch in the early 2030s, will carry advanced spectrometers to study the composition of Venus's surface, potentially identifying minerals that could only have formed in the presence of liquid water. Venera D, if realized, would be Russia's first mission to Venus since the Soviet era, symbolizing a return to its legacy of planetary exploration. The orbiter would conduct remote sensing of the atmosphere and surface, while the lander would gather data on the ground for longer than any previous Soviet mission. But the real future of Venus exploration may lie in the technologies NASA is developing: silicon carbide electronics, advanced phase change thermal systems, long-duration power supplies. If these technologies mature, we could have landers and even rovers operating on Venus for weeks or months. A seismometer operating on the surface for 60 days could detect Venus quakes, measure crustal movements, and determine whether Venus's interior is still molten. A rover could travel kilometers across the surface, studying different rock types and searching for evidence of past water. We could finally answer the fundamental question: is Venus dead, or is it still alive? Silicon carbide electronics, for instance, can withstand temperatures up to 600 degrees Celsius, far beyond the capabilities of traditional silicon-based systems. Phase change materials could absorb and release heat, maintaining stable internal temperatures even in Venus's extreme environment. Advances in power systems, such as Stirling engines or radioisotope generators, could provide sustained energy for landers and rovers. The story of Venus is far from over. It's a story of a world that was once different, a world that may have had oceans, a world that may have had a climate not unlike Earth's. Something changed. And until we understand what that something was, we won't fully understand our own planet's future. The fires of Venus may hold the key to our own survival. Venus, often dismissed as Earth's evil twin, may in fact be a mirror reflecting a possible fate for our own planet. Billions of years ago, Venus likely had a thinner atmosphere and surface temperatures that could have allowed liquid water to exist. Some scientists theorize that a runaway greenhouse effect, triggered by volcanic activity or other factors, led to the evaporation of its oceans and the thick carbon dioxide-rich atmosphere we see today. Understanding this process could provide critical insights into the long-term stability of Earth's own climate. Venus, with its slow retrograde rotation and lack of a global magnetic field, offers a stark contrast to Earth. Its day-night cycle lasts 117 Earth days, and its atmosphere is constantly stripped away by solar winds, leaving it vulnerable to further atmospheric loss. Yet, despite these differences, Venus remains our closest planetary neighbor, both in distance and in size. Its proximity to Earth makes it a practical target for robotic missions, with travel times as short as 4 months. As we continue to explore Mars and beyond, Venus stands as a reminder that the most profound discoveries may lie closer to home. The next generation of Venus missions could rewrite our understanding of planetary evolution and habitability, reminding us that even the most inhospitable worlds have stories to tell. Observation. The renewed interest in Venus is driven not only by technological advancements, but also by a growing recognition of its relevance to Earth. The planet's thick carbon dioxide atmosphere and extreme surface conditions serve as a cautionary tale about the potential consequences of unchecked climate change. By studying Venus, scientists hope to better understand the delicate balance that allows Earth to support life. Interpretation. The future of Venus. Exploration is poised to answer long-standing questions about the planet's past and present. Missions like Da Vinci Plus, Veritas, and Envision will provide unprecedented data on its atmosphere, surface, and interior, while new technologies could enable sustained exploration of its harsh environment. These efforts may reveal whether Venus was once habitable and shed light on the processes that transformed it into the hellish world we see today. Speculation. If Venus did once have oceans, it raises intriguing possibilities about the emergence of life. Could microbial life have evolved in its early waters? And if so, might remnants of that life still exist in its clouds or deep within its crust? The discovery of phosphine gas in Venus's atmosphere in 2020, a potential biosignature, has reignited debates about the planet's astrobiological potential. Future missions may seek to confirm or refute these findings, potentially revolutionizing our understanding of life in the universe. Part 5. The Clouds of Venus. In 1984, the Soviet Union launched two spacecraft called VeGa 1 and VeGa 2. The name is a portmanteau of Venera and Halley, the Russian word for Halley, because these spacecraft had a dual mission: drop probes at Venus, then continue on to fly past Halley's comet. Each VeGa spacecraft carried a lander similar to the Venera 13 and 14 design, but they also carried something new: balloons. The French space agency, CNES, had designed a balloon system specifically for Venus's atmosphere. The concept was to deploy a helium-filled balloon at an altitude of about 54 kilometers in the middle cloud layer, where temperatures are relatively moderate, around 40 degrees C, and pressures are only a few bars. The balloons were made of Teflon-coated fabric, about 3.4 meters in diameter when inflated. Each carried a gondola, weighing about 7 kilograms, equipped with instruments to measure pressure, temperature, wind speed, light levels, and atmospheric composition. The VeGa mission was one of the most ambitious and complex of its time. The spacecraft were designed to perform multiple tasks: delivering a lander to Venus's surface, deploying balloons into its atmosphere, and then journeying onward to rendezvous with Halley's comet, which was making its closest approach to Earth since 1910. The landers were equipped with instruments to analyze the soil composition, measure wind speeds, and capture the first-ever color images of the Venusian surface. The surface of Venus is a stark, inhospitable landscape, covered in volcanic rock and dust, with temperatures reaching over 490 degrees C, hot enough to melt lead. The pressure at the surface is a crushing 92 times that of Earth's sea level, comparable to the pressure found nearly a kilometer deep in the ocean. Meanwhile, the balloons were a groundbreaking experiment, marking the first time humanity had attempted to explore the atmosphere of another planet with floating probes. The Teflon coating on the balloons was chosen for its resistance to the corrosive sulfuric acid present in Venus's clouds, while the helium inside provided buoyancy in the dense carbon dioxide atmosphere. On June 11 and 15, 1985, the VeGa balloons were successfully deployed. They drifted with the Venusian winds, carried by the super-rotating atmosphere, completing nearly half a circuit around the planet over the course of 46 hours before their batteries ran out. The data they sent back was extraordinary. The balloons revealed that Venus's cloud layer is turbulent and dynamic. Vertical winds were stronger than expected, with updrafts and downdrafts exceeding 3 meters per second. These convective motions indicated that energy was being transported upward from the hot surface below, driving circulation in the clouds. The balloons also measured lightning, or rather, they detected electromagnetic signals consistent with electrical discharges. Lightning on Venus, if it exists, would not be visible to the human eye like it is on Earth. Instead, it would manifest as rapid discharges of energy within the dense, opaque clouds. Whether Venus has lightning comparable to Earth's thunderstorms remains debated, but the VeGa data suggested that electrical activity does occur in the clouds, possibly triggered by collisions between sulfuric acid droplets or by volcanic gases rising from the surface. The balloons also provided insights into the composition of Venus's clouds. The gondolas carried spectrometers that analyzed the chemical makeup of the atmosphere, confirming the presence of sulfuric acid droplets and measuring traces of other compounds like hydrogen sulfide and sulfur dioxide. These measurements helped refine models of Venus's atmospheric chemistry, revealing a complex interplay between solar radiation, volcanic activity, and chemical reactions. The data also suggested that the clouds are not uniformly distributed, but vary in density and composition across different regions of the planet. This heterogeneity could be linked to variations in surface activity, such as volcanism, which might release gases into the atmosphere in localized plumes. For example, the presence of sulfur dioxide in the upper atmosphere suggests recent volcanic eruptions, as this gas is quickly broken down by sunlight and must be replenished from below. Temperature fluctuations were also surprising. Over the course of a few hours, the balloons experienced temperature swings of several degrees, indicating that the atmosphere at that altitude is not stable or uniform. There are pockets of warmer and cooler air mixing and circulating in ways that weren't fully understood. The Vega balloon missions were a triumph of international cooperation. French engineers designed the balloons. Soviet engineers integrated them into the spacecraft, and tracking stations around the world monitored the signals as the balloons drifted around Venus. It was one of the few instances during the Cold War where space exploration brought nations together rather than driving them apart. The balloons transmitted data back to Earth using radio signals, which were picked up by ground stations in the Soviet Union, France, and other countries. This global effort highlighted the potential for scientific collaboration even amid geopolitical tensions. The Vega balloons were not the only probes to explore Venus's atmosphere. In 1978, the Pioneer Venus multiprobe mission, led by NASA, deployed 4 small probes into different regions of the Venusian atmosphere. These probes measured wind speeds, temperature, and pressure, providing a snapshot of conditions at various altitudes. One of the probes, the Day probe, entered the atmosphere on the planet's day side, while the others targeted the night side and intermediate regions. This mission revealed significant differences between the day and night sides of Venus, with the night side exhibiting higher wind speeds and more turbulent conditions. The data from Pioneer Venus complemented the Vega balloon findings, painting a more complete picture of Venus's atmospheric dynamics. For instance, the night side of Venus experiences wind speeds up to 60 times faster than the planet's rotation, a phenomenon known as superrotation. This rapid atmospheric circulation is one of the most intriguing mysteries of Venus's climate. But the story of Venus is not just a story of science. It's a story of speculation, of the unknown, and of the limits of human imagination. In 2012, a Russian scientist named Leonid Ksanfomolidi published an article claiming to have found evidence of life in the Venera images. He pointed to certain objects in photographs from Venera 13 that appeared to emerge, fluctuate, and disappear between frames. He suggested these could be living organisms adapted to Venus's extreme conditions. The objects included what he called a disk, a black flap, and a scorpion. According to Ksanfomolidi, their changing positions implied movement. Engineers familiar with the Venera probes quickly identified the disk as one of the ejected lens caps. There were 2 lens caps, and they landed in different places, creating the illusion of a single object that had moved. The other objects were attributed to image processing artifacts and noise. They don't appear in the original photography, only in enhanced versions. The Venera missions, launched by the Soviet Union between 1961 and 1983, were pioneering efforts to explore Venus. Venera 13 and 14, launched in 1982, were particularly successful, transmitting the first color images of the Venusian surface. These images revealed a barren, rocky landscape shrouded in a thick, hazy atmosphere. The probes also measured surface temperatures exceeding 460 C and pressures 90 times greater than Earth's sea level atmosphere. Despite these harsh conditions, the Venera missions laid the groundwork for future exploration of Venus, demonstrating the feasibility of landing spacecraft on its surface and operating scientific instruments in its extreme environment. For example, the Venera 13 lander survived for 127 minutes on the surface, sending back valuable data before succumbing to the heat and pressure. The scientific community largely dismissed these claims, but the episode raises an interesting question. Could life exist on Venus? Not on the surface, that much is certain. The temperature and pressure are too extreme, and there's no liquid water. But some astrobiologists have suggested that life could exist in the clouds at altitudes where conditions are more temperate. At 50 to 60 kilometers above the surface, the temperature is around 20 to 40 degrees C. The pressure is roughly 1 bar. Sulfuric acid droplets dominate, but there's also water vapor. In theory, microbial life could survive in these droplets using chemical energy from sulfur compounds or absorbing sunlight for photosynthesis. There's even some observational support for this idea. Measurements of sulfur dioxide concentrations in Venus's atmosphere show strange variations that are difficult to explain through chemistry alone. Some researchers have proposed that biological processes could be consuming or producing sulfur compounds, though this is highly speculative. The idea of life in Venus's clouds has gained traction in recent years, driven by advances in astrobiology and the discovery of extremophils on Earth, organisms that thrive in environments once thought inhospitable. For example, certain bacteria on Earth can survive in highly acidic conditions, such as the hot springs of Yellowstone National Park, where pH levels are comparable to those in Venus's clouds. Other microbes have been found living in aerosols in Earth's atmosphere, suggesting that life could potentially adapt to floating in droplets. While Venus's sulfuric acid clouds present a far more hostile environment, some scientists argue that life could have evolved unique adaptations to survive there, perhaps using sulfur compounds as an energy source. The concept of aerial biospheres, ecosystems suspended in the atmosphere, has been proposed for other worlds as well, including Jupiter's moon Europa and Saturn's moon Titan. In 2020, a team of scientists announced the detection of phosphine gas in Venus's clouds. Phosphine is a molecule that on Earth is produced almost exclusively by biological processes or industrial activity. Its presence on Venus, if confirmed, would be difficult to explain without invoking either unknown chemistry or biological sources. Phosphine is highly toxic and flammable, and its detection in Venus's atmosphere was initially met with excitement and skepticism. However, subsequent reanalysis of the data cast doubt on the detection. It's possible the signal was misinterpreted or contaminated by noise. As of now, the phosphine claim remains unresolved. The controversy highlights the challenges of studying Venus's atmosphere, which is opaque to most wavelengths of light, making direct observations difficult. The phosphine detection, if validated, would be a game-changer for our understanding of Venus and the potential for life beyond Earth. Phosphine is highly unstable in Venus's atmosphere and would be quickly destroyed by chemical reactions unless it were being continuously replenished. On Earth, phosphine is produced by anaerobic bacteria in oxygen-poor environments like swamps and sewage. If similar processes were occurring in Venus's clouds, it would suggest the presence of microbial life capable of producing phosphine as a metabolic byproduct. However, researchers have also explored non-biological explanations, such as volcanic activity or atmospheric chemistry involving phosphorus compounds. So far, no definitive explanation has emerged. The ongoing debate underscores the need for more sensitive instruments and future missions to Venus to unravel its mysteries. The point is this: Venus may not be completely dead. The clouds at least remain a place where we cannot rule out the possibility of life. It would be life unlike anything on Earth, adapted to float in sulfuric acid droplets. But the chemistry of life is remarkably flexible. Future missions carrying more sensitive instruments could settle the question, but for now, it remains an open mystery. Upcoming missions to Venus, such as NASA's Da Vinci Plus and ESA's Envision, aim to study the planet's atmosphere in greater detail. Da Vinci Plus, scheduled to launch in the late 2020s, will include a descent probe that will analyze the composition of Venus's clouds as it descends through the atmosphere. Envision, planned for the 2030s, will use radar to map the surface and study the planet's geological activity. Both missions could provide critical data to assess the habitability of Venus's clouds and search for signs of life. Until then, Venus remains a world of endless fascination, a testament to the mysteries that still lurk in our own solar system. Its thick, swirling clouds continue to guard their secrets, beckoning scientists and dreamers alike to uncover the truth hidden within. Part 6. The Final Frontier. The last Soviet probe to reach Venus's surface was Venera 14 in 1982. The probe transmitted data for 57 minutes, capturing panoramic images of the barren, rocky landscape before succumbing to the planet's crushing pressure and temperatures exceeding 450 degrees Fahrenheit. The images revealed a stark, desolate world with flat volcanic plains stretching to the horizon under a perpetually orange, hazy sky. The Vega missions in 1984 were the final hurrah, delivering balloons to float in the upper atmosphere and study the planet's weather patterns. These balloons, carried by winds moving at over 200 kilometers per hour, transmitted data for 2 days, revealing turbulent conditions and surprising chemical compositions in the clouds. But after Vega, nothing for decades. Why? Part of the answer is economics. The Soviet Union was facing increasing financial strain in the 1980s, with the cost of the Afghanistan war alone reaching $3 billion annually. By 1989, the Soviet economy was in freefall, with inflation rates exceeding 10% and foreign debt rising to unsustainable levels. Space exploration, while prestigious, was expensive. Venus missions, with their complex engineering requirements and high failure rates, were particularly costly. Each Venera mission cost hundreds of millions of dollars in today's terms, and the failure rate was over 50%. The Venera 13 and 14 missions, for instance, each required over $300 million in today's currency to design, build, and launch, and their success was far from guaranteed. By the mid-1980s, Soviet priorities were shifting. The Mir space station program, which would eventually cost over $4 billion, was taking up resources. Plans for Mars missions were being drawn up, culminating in the failed Mars 96 mission, which carried an estimated price tag of $300 million. Venus fell out of favor. The collapse of the Soviet Union in 1991 essentially ended Russia's planetary exploration program for years. Budgets were slashed, with space spending dropping by over 80% in the 1990s. Expertise was lost as engineers retired or moved to other fields. The infrastructure that had supported the Venera program decayed, with facilities like the Baikonur Cosmodrome falling into disrepair. Meanwhile, NASA's focus had shifted to Mars. The Viking landers in 1976 had captured the public imagination with their color images of the Martian surface and tantalizing hints of past water. Mars seemed more hospitable, more Earth-like, more likely to have hosted life. The planet's thin atmosphere and accessible surface made it a more practical target for exploration. Venus, by comparison, seemed like a dead end. There was also a technological barrier. The Venera missions had pushed 1970s and 1980s technology to its absolute limit. To go beyond 2 hours of surface operation would require fundamentally new approaches, new materials, new electronics, new power systems. Those technologies didn't exist yet, so Venus was left alone. The harsh conditions on Venus meant that even flybys were challenging. The Magellan mission in the early 1990s mapped 98% of the planet's surface using radar, revealing vast volcanic plains, towering mountain ranges, and enigmatic coronae, circular structures that hinted at past geological activity. But it couldn't penetrate the thick clouds to study the atmosphere or surface in detail. The Pioneer Venus missions in the late 1970s had dropped probes into the atmosphere, but their data was limited, and many questions remained unanswered. But the story of Venus is not just a story of the past, it's a story of the future. NASA has announced 2 missions to Venus launching later this decade. Da Vinci Plus, the Deep Atmosphere Venus investigation of noble gases, chemistry, and imaging, will drop a probe through the atmosphere in 2031. During its hour-long descent, it will analyze trace gases, water vapor, temperature, and pressure, providing unprecedented insights into the planet's atmospheric composition. Its instruments will be so sensitive that they could detect gases present in parts per billion, offering clues to the planet's past and present climate. In its final 20 minutes, as it falls through the cloud deck, it will photograph a highland region called Alpha Regio before impacting the surface. This region, known for its tesserae terrain, ancient deformed landscapes, may hold clues to the planet's geological history. Veritas, the Venus Emissivity, Radioscience, INSAR, Topography and Spectroscopy mission will use radar to map Venus's surface in far higher resolution than ever before, creating detailed 3D relief maps. It could identify safe landing sites for future missions, as well as detect signs of past or present volcanic activity. Its synthetic aperture radar will be so advanced that it could resolve features as small as 30 meters across, revealing details that have eluded scientists for decades. The European Space Agency has approved Envision, a radar mapping orbiter that will study Venus's surface composition and internal structure. Launching in the early 2030s, it will carry a suite of instruments, including a sounder to probe beneath the surface and spectrometers to analyze the chemical makeup of the rocks. Russia has been discussing Venera D, a return to Venus that would include both an orbiter and a lander. The lander would have a mission lifetime of about 3 hours based on battery capacity and traditional thermal management, but it would carry modern instruments, including a mass spectrometer and cameras capable of operating in Venus's harsh environment. Its goal would be to measure the composition of the rocks and atmosphere with unprecedented precision, shedding light on the planet's evolution. But the real future of Venus exploration may lie in the technologies NASA is developing. Silicon carbide electronics designed to withstand temperatures up to 500 degrees C, advanced phase change thermal systems to regulate heat, and long-duration power supplies like nuclear batteries. If these technologies mature, we could have landers and even rovers operating on Venus for weeks or months. A seismometer operating on the surface for 60 days could detect Venus quakes, measure crustal movements, and determine whether Venus's interior is still molten. A rover could travel kilometers across the surface, studying different rock types and searching for evidence of past water. One proposed rover design, the Automaton Rover for Extreme Environments, AREE, would use a clockwork mechanism to operate without electronics, surviving for months in the harsh conditions. Another concept, the Venus Land Sailing Rover, would harness the planet's winds to propel itself across the surface, exploring vast distances over time. We could finally answer the fundamental question: is Venus dead, or is it still alive? The answer could have profound implications for our understanding of planetary evolution. If Venus is still geologically active, it could mean that terrestrial planets can remain dynamic for billions of years, even under extreme conditions. The story of Venus is far from over. It's a story of a world that was once different, a world that may have had oceans, a world that may have had a climate not unlike Earth's. Something changed. Scientists believe that around 700 million years ago, a runaway greenhouse effect transformed Venus from a potentially habitable world into the hellish landscape we see today. This process may have been triggered by a combination of volcanic activity, changes in solar radiation, and the loss of the planet's magnetic field. And until we understand what that something was, we won't fully understand our own planet's future. The fires of Venus may hold the key to our own survival. As Earth's climate warms and atmospheric carbon dioxide levels rise, some scientists warn that we could be on a similar path. By the end of the century, Earth's average temperature could increase by as much as 4 degrees Celsius if current trends continue, pushing us closer to the tipping point that Venus crossed long ago. Venus serves as a stark reminder of what can happen when a planet's climate spirals out of control, but it also offers hope. If we can unravel the mysteries of Venus, we may learn how to avoid a similar fate. The future of Venus exploration is not just about understanding another world. It's about understanding our own. Observation. The renewed interest in Venus is driven not only by scientific curiosity, but also by a sense of urgency. As climate change accelerates on Earth, Venus provides a unique laboratory for studying the extreme outcomes of a runaway greenhouse effect. Interpretation. The technologies being developed for Venus exploration, such as high-temperature electronics and advanced thermal management systems, could have applications far beyond planetary science. They could revolutionize industries like aerospace, energy, and manufacturing, where extreme environments are common. Virtis speculation. If future missions discover evidence of past water or ongoing geological activity on Venus, it could rewrite our understanding of habitability in the solar system. Venus might not be a dead world, but a dormant one, with lessons that stretch far beyond its scorched surface. Part 7. Hidden Propulsion. The Soviet Venera missions were an achievement that deserves more recognition than it gets. In the West, they were overshadowed by the space race to the Moon and the Viking landers on Mars. But in terms of pure engineering difficulty, landing on Venus and operating there for even a few minutes was as impressive as anything NASA accomplished. The surface of Venus is a hellish landscape, with temperatures reaching 870 km, 425 degrees, a pressure 90 times that of Earth's sea level, and clouds of sulfuric acid. The last signals from Venera 13 and 14 faded out in 1982, but their legacy remains indelible. The landers are still there on the plains of Venus, slowly being corroded by the atmosphere. Their final images revealed a stark, rocky terrain unlike anything seen elsewhere in the solar system. One day, perhaps a future mission will find them, these ancient artifacts of humanity's first steps onto another world's surface. For now, they rest in the heat and the darkness and the crushing pressure, monuments to what humans can achieve when we refuse to accept that something is impossible. The Venera missions proved that even in the most hostile environment we know of, it's possible to survive long enough to learn something. Every rock in those photographs tells a story. Every crack in the ground is a clue. Venus was once different. It may have had oceans. It may have had a climate not unlike Earth's. Something changed. And until we understand what that something was, we won't fully understand our own planet's future. The data from Venera 13 and 14 suggested that the rocks on Venus were likely basaltic, similar to the volcanic rocks found on Earth. This hinted at a violent geological past, with volcanic activity reshaping the planet's surface over billions of years. But the story of Venus is not just a story of the past, it's a story of the future. NASA has announced 2 missions to Venus launching later this decade. Da Vinci Plus, the deep atmosphere Venus investigation of noble gases, chemistry, and imaging, will drop a probe through the atmosphere in 2031. During its hour-long descent, it will analyze trace gases, water vapor, temperature, and pressure. Its findings could revolutionize our understanding of Venus's atmospheric composition and the processes that have shaped it over time. In its final 20 minutes, as it falls through the cloud deck, it will photograph a highland region called Alpha Regio before impacting the surface. These images might reveal geological structures that hint at Venus's ancient history, including possible evidence of past tectonic activity. Veritas, the Venus Emissivity, Radioscience, INSAR, Topography, and Spectroscopy mission will use radar to map Venus's surface in far higher resolution than ever before, creating detailed 3D relief maps. It could identify safe landing sites for future missions, as well as uncover geological features that were previously hidden beneath the planet's thick clouds. The European Space Agency has approved Envision, a radar mapping orbiter that will study Venus's surface composition and internal structure. Its instruments will probe beneath the surface, revealing the planet's tectonic history and the processes that led to its current state. Russia has been discussing Venera D, a return to Venus that would include both an orbiter and a lander. The lander would have a mission lifetime of about 3 hours, based on battery capacity and traditional thermal management. This brief window could still provide invaluable data about the conditions on the surface and the chemical makeup of the rocks. But the real future of Venus exploration may lie in the technologies NASA is developing: silicon carbide electronics, advanced phase-change thermal systems, long-duration power supplies. These innovations could transform our approach to Venus, allowing us to design landers and even rovers capable of operating in its extreme environment. If these technologies mature, we could have landers and even rovers operating on Venus for weeks or months. A seismometer operating on the surface for 60 days could detect Venus quakes, measure crustal movements, and determine whether Venus's interior is still molten. These vibrations would provide insight into the planet's geological activity and the forces shaping its surface. A rover could travel kilometers across the surface, studying different rock types and searching for evidence of past water. It might even discover remnants of ancient oceans, preserved in the chemical signatures of the rocks. We could finally answer the fundamental question: is Venus dead, or is it still alive? The story of Venus is far from over. It's a story of a world that was once different, a world that may have had oceans, a world that may have had a climate not unlike Earth's. Today, Venus orbits the Sun at a distance of about 108 million kilometers, closer than Earth, but still within the habitable zone where liquid water could theoretically exist. Its orbit is slightly elliptical, with a year lasting approximately 225 Earth days. However, due to its slow rotation, a day on Venus is longer than a Venusian year, taking about 243 Earth days to complete one rotation on its axis. Its retrograde rotation, spinning in the opposite direction to most planets, adds another layer of mystery to its evolutionary history. The planet's thick, toxic atmosphere, shrouded in perpetual cloud cover, reflects over 75% of the sunlight that reaches it, yet the intense greenhouse effect traps enough heat to make it the hottest planet in the solar system. As we look to the future, Venus stands as both a cautionary tale and a source of inspiration. Its harsh environment challenges us to push the boundaries of technology and engineering, while its mysterious past urges us to unravel the secrets of planetary evolution. The next generation of missions to Venus will not only expand our scientific knowledge, but also remind us of the fragility of our own world. The lessons we learn from Venus could shape our understanding of climate change, geological processes, and the delicate balance that sustains life on Earth. In the coming decades, humanity's return to Venus will mark a new chapter in our exploration of the solar system, one that could redefine our place in the cosmos and our responsibility to protect the only home we've ever known. The Venera landers were a testament to human ingenuity, but they were just the beginning. Their successors, the future missions to Venus, will be more advanced, more resilient, and more revealing. They will carry the hopes and aspirations of a new generation of scientists and engineers determined to unlock the secrets of our sister planet. As we delve deeper into the mysteries of Venus, we will not only learn about its past and present, but also gain insights into our own future. The fires of Venus may hold the key to our own survival. Its thick atmosphere, composed primarily of carbon dioxide, traps heat through the greenhouse effect, creating a runaway warming process that has transformed the planet into the inferno we see today. Understanding this process could offer critical insights into Earth's climate and the potential consequences of unchecked greenhouse gas emissions. The journey to Venus is not just a scientific endeavor, it is a journey of discovery, a quest to understand the universe and our place within it. The data gathered by these missions will rewrite textbooks, inspire new theories, and pave the way for even more ambitious explorations. The story of Venus is a story of resilience, of a planet that has endured cataclysmic changes and emerged as a living testament to the forces of nature. As we uncover its secrets, we will not only gain a deeper understanding of the cosmos, but also a greater appreciation for the fragile beauty of our own world. The fires of Venus burn brightly, a beacon of knowledge and a reminder of the power of human curiosity and determination. Part 8. The End of the Beginning. The last Soviet probe to reach Venus's surface was Venera 14 in 1982. The Vega missions in 1984 were the final hurrah, and then nothing for decades. Why? Part of the answer is economics. The Soviet Union was facing increasing financial strain in the 1980s. Space exploration, while prestigious, was expensive. Venus missions, with their complex engineering requirements and high failure rates, were particularly costly. The Venera 15 and 16 orbiters, launched in 1983, cost approximately $500 million in today's dollars, a staggering investment for the time. By the mid-1980s, Soviet priorities were shifting. The Mir space station program, launched in 1986, was taking up resources, ultimately costing over $4 billion during its lifespan. Plans for Mars missions, such as the ambitious but ultimately failed Mars 96 orbiter, were being drawn up. Venus fell out of favor. The collapse of the Soviet Union in 1991 essentially ended Russia's planetary exploration program for years. Budgets were slashed, with Russian space spending dropping by over 80% in the decade following the collapse. Expertise was lost as engineers retired or moved to other fields. The infrastructure that had supported the Venera program decayed, with many facilities falling into disrepair. The once thriving Soviet space program, which had achieved remarkable feats like the first human in space and the first spacewalk, was reduced to a shadow of its former self. But the story of Venus is not just a story of the past, it's a story of the future. NASA has announced 2 missions to Venus launching later this decade. Da Vinci Plus, the deep atmosphere Venus investigation of noble gases, chemistry, and imaging, will drop a probe through the atmosphere in 2031. During its hour-long descent, it will analyze trace gases, water vapor, temperature, and pressure, providing unprecedented insights into the chemical makeup of Venus's atmosphere. The probe will carry 7 separate instruments, including a mass spectrometer to measure atmospheric composition and a tunable laser spectrometer to detect trace gases like sulfur dioxide and water vapor. In its final 20 minutes, as it falls through the cloud deck, it will photograph a highland region called Alpha Regio before impacting the surface. Veritas, the Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy mission will use radar to map Venus's surface in far higher resolution than ever before, creating detailed 3D relief maps. It will orbit Venus 65 times over 2 Venusian days, approximately 487 Earth days, using synthetic aperture radar to penetrate the thick clouds and map the surface with a resolution of up to 30 meters per pixel. It could identify safe landing sites for future missions and detect plate tectonics or volcanic activity, revolutionizing our understanding of Venus's geology. The European Space Agency has approved Envision, a radar mapping orbiter that will study Venus's surface composition and internal structure, building on data from previous missions like NASA's Magellan, which mapped 98% of Venus's surface between 1990 and 1994. Envision will carry 5 advanced instruments, including a ground-penetrating radar to study subsurface structures and a spectrometer to analyze surface minerals. Russia has been discussing Venera D, a return to Venus that would include both an orbiter and a lander. The lander would have a mission lifetime of about 3 hours based on battery capacity and traditional thermal management, aiming to surpass the longevity of previous Venera missions, which survived for a maximum of 127 minutes on the surface. The orbiter component of Venera D would conduct global monitoring of Venus's atmosphere and surface for up to 3 years, providing valuable context for the lander's findings. If funded, Venera D could launch as early as 2029, marking Russia's return to Venus after more than 4 decades. The lander would carry a suite of instruments, including cameras, gas chromatographs, and sensors to measure atmospheric pressure, temperature, and wind speeds. Its design would incorporate lessons learned from the Venera 13 and 14 missions, which returned the first color images from Venus's surface in 1982. But the real future of Venus exploration may lie in the technologies NASA is developing. Silicon carbide electronics, advanced phase-change thermal systems, long-duration power supplies. If these technologies mature, we could have landers and even rovers operating on Venus for weeks or months. A seismometer operating on the surface for 60 days could detect Venus quakes, measure crustal movements, and determine whether Venus's interior is still molten, much like how NASA's InSight lander has studied Mars's seismic activity since 2018. InSight has detected over 1,300 Marsquakes, providing unprecedented insights into Mars's internal structure. A Venus seismometer could reveal whether Venus has a solid or liquid core, a question that has long eluded scientists. A rover could travel kilometers across the surface, studying different rock types and searching for evidence of past water, potentially discovering signs of ancient hydrothermal systems or mineral deposits that could only form in the presence of liquid water. The Soviet Venera missions found rocks like granite and basalt on Venus's surface, suggesting a complex geological history. A future rover could analyze these rocks in greater detail using instruments like X-ray diffraction and laser-induced breakdown spectroscopy to determine their precise composition and origin. The story of Venus is far from over. It's a story of a world that was once different, a world that may have had oceans, a world that may have had a climate not unlike Earth's. Something changed, and until we understand what that something was, we won't fully understand our own planet's future. The fires of Venus may hold the key to our own survival. Venus is often called Earth's sister planet due to its similar size and composition, but its atmosphere is a stark reminder of how quickly a habitable world can become uninhabitable. With surface temperatures reaching 800 465 C, and pressures 90 times greater than Earth's, Venus is a cautionary tale of a runaway greenhouse effect. Its atmosphere is 96% carbon dioxide, trapping heat and creating a suffocating blanket that has boiled away any water that once existed on its surface. The cloud layers of Venus, composed of sulfuric acid droplets, reflect about 75% of the sunlight that reaches the planet, contributing to its intense heat retention. The atmosphere's circulation is driven by winds that can reach speeds of up to 220 miles per hour, 360 kilometers per hour in the upper layers, creating a dynamic but inhospitable environment. Finale, the fire. Next time. The fires of Venus are not just a warning from the past, they are a glimpse into a possible future, one that could belong to Earth if we fail to heed the lessons of our sister planet. Venus was once different. It may have had oceans, it may have had a climate not unlike our own, but something changed, and that something was catastrophic. The runaway greenhouse effect that transformed Venus into a hellscape is a cautionary tale for our own world. As we grapple with climate change, as we push the boundaries of what our atmosphere can endure, we must remember Venus. It is a mirror held up to our own future, a future that could be written in fire if we are not careful. Earth's atmosphere is currently warming at an alarming rate, with global temperatures increasing by approximately 1.1 since the pre-industrial era. If this trend continues unchecked, Scientists warn that Earth could experience a runaway greenhouse effect similar to Venus's, though on a much slower timescale. The consequences would be devastating: rising sea levels, extreme weather events, and the collapse of ecosystems that sustain life. The last signals from Venera 13 and 14 faded out in 1982. The landers are still there on the plains of Venus, slowly being corroded by the atmosphere. One day, perhaps a future mission will find them, these ancient artifacts of humanity's first steps onto another world's surface. For now, they rest in the heat and the darkness and the crushing pressure, monuments to what humans can achieve when we refuse to accept that something is impossible. The Venera landers were engineering marvels, designed to withstand conditions that would destroy most spacecraft in minutes. Their legacy lives on in modern missions, inspiring engineers to push the boundaries of what is possible in the harshest environments imaginable. The Venera 13 and 14 landers were equipped with spring-loaded arms that allowed them to sample the soil and drill into the surface, providing the first direct measurements of Venus's geology. Their cameras captured panoramic views of the alien landscape, revealing a rocky, barren world shrouded in a perpetual haze. But the story of Venus is not over. It is a story of perseverance, of ingenuity, and of the relentless human drive to understand the universe. It is a story of a world that was once different, a world that may have had oceans, a world that may have had a climate not unlike Earth's. Something changed. And until we understand what that something was, we won't fully understand our own planet's future. The fires of Venus may hold the key to our own survival and the key to unlocking the mysteries of the cosmos. Venus challenges us to confront the fragility of habitability and the consequences of unchecked climate change. Its story is not just one of scientific curiosity, but of existential urgency. The planet's thick clouds, once thought to hide vast oceans, were revealed by the Mariner 2 mission in 1962 to be composed of sulfuric acid, dashing hopes of a habitable Venus. Since then, scientists have been grappling with the question of how Venus became the way it is today and what lessons its fate holds for Earth. The final question remains: is Venus dead, or is it still alive? The answer may lie buried in the rocks, in the clouds, or in the supercritical ocean that covers its surface. Future missions will search for the truth, but for now, Venus remains a world of fire and mystery, a world that challenges us to confront the limits of our own imagination. Every new mission to Venus, from the early Mariner flybys to the upcoming Da Vinci Plus and Veritas probes, represents a step forward in our understanding of this enigmatic planet. Each discovery brings us closer to solving the riddle of Venus, and perhaps, in doing so, to securing our own future. The Japanese Aerospace Exploration Agency's Akatsuki orbiter, which arrived at Venus in 2015, has already detected unusual atmospheric phenomena, such as fast-moving cloud structures and a massive stationary gravity wave in the upper atmosphere. These findings suggest that Venus's atmosphere is far more dynamic than previously thought, raising new questions about its past and present. And so, the story of Venus ends as it began, with a question. What if the future of our own planet is written in the fires of Venus? The answer may be closer than we think. As we look to the skies, we are reminded that the fate of Earth and Venus are intertwined. The choices we make today will determine whether our planet follows the path of its sister world or forges a new destiny among the stars. The fires of Venus burn brightly, a beacon of both warning and hope, illuminating the path forward for humanity. The planet's hellish conditions are a stark reminder of the delicate balance that makes life possible on Earth, and the consequences of disrupting that balance. As we continue to explore Venus, we not only uncover the secrets of another world, but also gain a deeper understanding of our own. The future of Venus exploration is bright, with missions like Da Vinci Plus, Veritas, Envision, and possibly Venera D on the horizon. Each of these missions will build upon the legacy of the Venera program, pushing the boundaries of what is possible and expanding our knowledge of this enigmatic planet. The story of Venus is far from over. It is a story of discovery, resilience, and the enduring human quest to understand our place in the cosmos.